So welcome to the channel guys, and today we will see how we can write the input script for in LAMMPS to calculate the radial distribution function for a material. So today I will be using argon gas to calculate its radial distribution function, and I will find the RDF or radial distribution function for solid argon. But before that, let us look at what is a radial distribution function. So let us consider that this is an apple tree, and these are some apples that has fallen on the ground. Now let us draw some spherical shells around these apples. Okay, and now what is RDF? So RDF is basically uh, tells us about the probability of finding an apple in a shell that is at a distance r from a reference atom. Okay, so or a reference apple, whatever it is. So if this is the shell, okay, and there are some apples you can see in this shell. So RDF is the probability of finding the apples in this spherical shell that is at a distance r. Let us say this distance from the trunk of the apple tree, or our central reference atom. So at a distance r from the reference atom. Okay, so it also tells us about the how closely the atoms in the system are packed together. Okay, so to to construct an RDF is very simple. Let us consider that this is a system containing some number of atoms. So what we do, we uh, choose atom in the system, and draw a series of concentric spheres around this atom. So these are the spherical shells. Okay, like 1 2 3 4, these are the different shells, or we can call them as wings when we will write them script in lamps. And the distance between these spherical cells is delta r. Okay, so g of r is a radial distribution function, and its formula is nr. Basically n is basically the average number of atoms in each shell or win, is divided by rho. Rho is the average density of atoms in the system, and this is the volume of each shell. Okay, so we will we will find the RDF for a different value of r. Okay, for different value of r we will find the radial distribution function. So now we will discuss the input script to find the RDF of solid argon. In this video, from units metal to up to time step 0.001, uh, I am not going to discuss this part. That is because I have already made a video on how we can write input script in LAMMPS, and this part of this input script is already discussed there. Okay, so it is very basic, and just go to that video by clicking the notification above, and watch this video. Just relax, and after watching the video, come to this video and start watching from compute. Okay, so now the compute here, is used to calculate the RDF of the organ. Okay, so let us go to the LAMMPS documentation and let us look at the compute RDF command. Okay, so this is the syntax of the compute RDF command. So this is compute, this is simply the ID, that is user generated ID. This is group ID and this is the RDF style name. Okay, so let us go to the script and so this is the user generated ID and this is all. So I have not defined any group in my script as we have only single type of atom, that is orgon. So that's why by default I am writing all here. This is the RDF style name, and after that comes the number of wins. Okay, so number of wins or number of spherical shells that I am using in my input script. Okay, so it is 100, so that's why uh, yeah, it is 100. Okay, and this is 1 1, so I have only single type of atom, that is why this is 1 1, and this is the cutoff distance, that is 10 angstroms. So up to 10 angstroms I will be calculating the RDF for orgon. Okay, and after that, if you see, uh, the simplest way to output the result of the compute RDF calculation to a file is to use fix average time command. Okay, so with the compute command I am also going to use the fix average time command. Okay, so let us look at this command. So this is the syntax of fix average time command, and this is fix, this is user generated ID, this is the group ID, and this is the style. Okay, so there is no need to worry about that. Fix user generated ID, this is the group ID, that is by default all, and this is average per time, that is the name of the style. Okay, now now come the three numbers here, as you can see. Now what is this? Let us understand it through the example here. Okay, so there is an example. Okay, so this is, and every it is 2 and repeat 6, and frequent is that is 100. Okay, so 100 basically the number of time steps. Okay, in our case this is 10,000 time steps, that is I am going to run, for which I am going to run my simulation. And after that and repeat equal to 6. So what does this mean? That there are going to be 6 values on time steps: 90, 92, 94, 96, 98, and 100. And why these values are? Because uh, we want the values on these time steps after every two iteration, or after every two time steps. Okay, so on these 6 time steps, whatever value I will get will be used to compute the final average. Okay, so in my case it is 10,000, and it is also here 10,000. So whatever value I will get, uh, so for every 10,000, for every time step, actually in our case, on every time step, whatever value we are getting is used to calculate the average on, like here it is average on time step 100. So average on time step 10,000 time steps. Okay, so simply mean that whatever value we are getting is going to be used to calculate the average quantity. That is why it is written 1 here. Every value should be used, okay, to calculate the final average quantity. After that if you see, uh, the compute RDF command, the compute RDF command actually calculates a global array with the number of rows equal to number of wins. So in my case, number of wins is 100, or the number of spherical cells. So uh, the number of rows will be 100. Okay, and the number of columns will be 1 plus 2 multiplied by n pair. So only I have a single pair of atoms, so there are going to be 3 columns. Okay, so the first column basically tell tells us about the distance. Okay, the distance r from one atom to the another atom, and after that we will get the second column will give the value of RDF, and the third column will give the value of coordination number. Okay, so it will give the value of distance at which we are calculating the RDF, and it will give the value of RDF, and it is going to give the value uh, of coordination number, and all this data is going to store in the file name arrdf underscore solid dot txt. Okay, and the mode is vector. So the mode is vector, and what does this mean? That whatever our input values are, they will be stored in the form of vectors or arrays. Okay, after that, this is the dump, and this is dump id with the default group all, and every 100 step I want to store the data in dump file. This is the dump file, and what I want to store is the id of the atoms, type of atoms. Oh my god, what is this? Yeah, okay, so this is the id, this is the type, and these are the position and velocities of the atoms with the time evolution. This is there I am performing the NBE integration, and this is the thermostyle. Basically what I want to print in the log file. Okay, so I want to print the information in the log file for every 1000 steps. I will run the simulation for 10,000 steps, uh, or 10 picoseconds. Okay, when I multiply 10,000 by 0.001, I get 10 picoseconds. After that I unfix and undo. Okay, so when I run this input script, then what I'm going to get an additional file of argon rdf underscore solid dot txt. Okay, so this is the file, and okay, this is the file. Now let us go through this file. So it is not clearly visible, but let me tell you, it is starting from here, and we have total number of 100 rows. Okay, so these are the 100 rows. Okay, and basically we have 3 columns. Okay, the first one is nothing what uh, first the first column is nothing what the serial number, and after that this is the distance at which the RDF is calculated. This is the value of RDF, and this is the value of coordination number. Okay, so the graph of RDF we are going to draw is between this value and this value, or between the column first and the column second. Okay, the column first and the column second. So let us go through the graph, then discuss whatever it is. Okay. Mm. So this is the graph of oh my god, what is this? I'm sorry, where is the graph? Mm, mm. Yeah, this is the graph. Okay. So this is the graph of RDF of solid argon. Okay. So on the vertical axis, this is the RDF. Okay. And on the x-axis, this is the value of distance. Okay. Distance from the reference atom. Okay. Now if we go through the graph, so you can see that after some distance, uh, there are some peaks. Okay, you can see some peaks are here. Okay, so what is the meaning of this? That after some distance, let us say some number, this distance is in angstroms. Okay, so it will be around 3 point something. We are getting the highest peak in the graph. So at this distance we have the probability, or we have the maximum number of atoms at this distance from our reference atom. Okay, and after that we have also small peaks. Okay, so at different value of distance we are getting some number of atoms. Okay, so this is in the case of solid argon. Okay, and if the same RDF can be calculated for liquid and liquid argon and argon in its gaseous state. Okay, so you can calculate for liquid and in its gaseous form, and the graph, you can find those values just by changing the temperature here. Okay, argon is mostly solid at this temperature, that's why this temperature has been used. If you change the value of temperature, you can calculate the value of RDF of argon for various different value of temperatures. And when you will draw the graph for liquid and in for its gaseous phase, then the graph is not going to be similar. Okay, so because in case of solid there is a maximum probability of finding the atoms at a particular distance, but in case of liquid and in case of gas, as we have more randomness. Okay, so the particles at very large distance. So in case of liquid and gas, if you look at the RDF, these peaks after some distance will vanish. Okay, and it will go straight. Okay, so you can do that just by changing the value of temperature here and draw these graphs. Okay, thank you.